Imagine being able to take a simple text prompt, a single image, or a short video clip, and instantly turning it into a fully dynamic, moving 3D object. This is the promise of 4D generation, which adds the dimension of time to 3D assets. However, training models to do this from scratch is incredibly difficult due to the lack of massive, paired 4D datasets. Align4D solves this by taking a modular approach. Instead of training a massive model from scratch, it leverages existing, highly capable off-the-shelf models to generate a synchronized video, 3D pair, and then focuses entirely on aligning them. When we try to combine independent video and 3D models, we run into a major roadblock. They do not share the same spatial coordinate system. Video models capture objects at a fixed distance, while 3D diffusion models expect canonical scales. If these distances do not match, the generated 4D object suffers from floating artifacts, distortion, or severe blur. To make these models talk to each other, we must find a way to mathematically align their spatial perspectives. To solve this spatial mismatch, the researchers developed a clever technique called object distance alignment. It automatically searches for two critical distances. First, the video-aligned object distance, or VAOD, uses mean squared error to match front-view renderings of the 3D model with the actual video frames. Second, the multi-view-aligned object distance, or MAOD, uses scored distillation sampling loss to find the distance that best fits the multi-view diffusion model's internal prior. Finding these exact distances is the key to clean, artifact-free rendering. Once the correct distances are established, the next step is ensuring the object moves naturally while keeping its shape consistent from every angle. This is where motion geometry joint alignment comes in. For known viewpoints, like the front view, the model strictly aligns with the input video. For unknown viewpoints, it uses a single multi-view diffusion model conditioned on the video frames. This allows the system to seamlessly transfer motion and geometry priors to non-front views without relying on unstable multi-model optimization. Optimizing both the 3D shape and the motion network at the same time is notoriously unstable, often leading to a chaotic mess. To prevent this, Align4D introduces asynchronous optimization. Instead of updating everything at once, the training process alternates. It fixes the 3D Gaussian splatting attributes while training the deformation network, and then fixes the deformation network while refining the 3D geometry. This decoupling ensures stable convergence and preserves high-fidelity details. To rigorously test this new approach, the authors had to build a brand new benchmark because no comprehensive dataset existed for this task. They created X4D, the first quadruple dataset containing aligned text, image, video, and 3D assets. They built it using 4 complementary pipelines, ensuring that whether you start with a text prompt, a single image, a video, or a 3D model, there is a high-quality, aligned ground truth to compare against. Let's look at how Align4D performs in practice compared to existing state-of-the-art methods. In qualitative evaluations, Align4D consistently generates highly detailed, geometrically consistent 4D targets that faithfully replicate the video's motion. Quantitative results on both the X4D and consistent 4D datasets show that Align4D outperforms baselines across key metrics, including PSNR, SSM, and human preference studies. While Align4D represents a massive leap forward, it isn't without its hurdles. Because it relies on off-the-shelf models, it inherits their limitations, such as struggling with transparent materials or rapidly flickering neon effects. However, as foundational video and 3D models continue to improve, Align4D's modular framework is perfectly positioned to adopt these upgrades, paving the way for highly realistic 4D content creation in gaming, virtual reality, and cinema.